Hi, everyone, and welcome to this next algebra video. In this one, I want to continue talking about the basics of the functions and relations and equations and graphs in general. So I'm going to start with a few definitions, and then we'll move on to working through a handful of problems. So the first definition I have here is a relation. Now, relation is a very general term. Basically, and every equation out there, if it's got an equal sign, some letters, and some numbers, it's a relation. So a relation is a well-defined method, rule, or set of rules that describes how two sets of objects are paired up. Now, in an algebra class, it's usually given as an equation. So let's say, for example, 3 minus 2x is equal to 4 minus y, right? That's an equation that connects these two sets, the set of all x values and the set of all y values. Y equals 3x squared plus 1. That's another relation. These two relations are also functions, which we'll talk about in a moment or two. A relation could also be given, let's do one more equation that's not a function, x squared plus y squared equals 9. Okay, so that's another relation. It could be a list of objects on the left and a list of objects on the right with arrows connecting them. It could be a set of points. There's a lot of different ways a relation could be given. But the point is, the point here is you have two sets. You have the first set and the second set. Again, in an algebra class, generally, the first set is going to be the set of x values, and the second set is going to be the set of y values, but that doesn't have to be true. Okay, next definition, more specific than relation, is a function. So a function, it's a specific type of relation. So we're going to do a couple of problems where I give you a relation, and I say, okay, is this a function, yes or no? And it comes down to this definition. If a relation is structured in such that each member of the first set is paired up with exactly one member of the second set, then we say it's a function, right? Each x value could pair up with only one y value, not two. So for an equation to be a function, no x value could have more than one y value. We'll talk more about that when we start working through a couple of problems. The next definition, related to functions. Remember, a relation connects two sets. A function is a type of relation, so it connects two sets. The set of all independent values or input values or x values, the first set, right? I'm going to stop saying first set and second set. We have specific names for these. The domain is the set of all x values or the set of all independent or input values. And the range is the set of all y values or dependent values or output values. So these words, dependent, output, y value, range, they all go together. And independent, input, x values, domain, they go together. Okay, next definition. I'll give two definitions at once. The graph. So I didn't underline the second one, the graph. So we're going to be talking about graphs. And in an algebra class or a pre-calculus class, we're going to be talking about graphs pretty extensively. And so there's two different contexts, two different ways we can talk about graphs, the graph of an equation and the graph of a function. We have two different ways of talking about numbers. We could use decimals or we could use fractions. There's two different ways of describing more or less the same thing. When we're graphing equations, well, that's they're not exactly the same, right? Because I would say they're not exactly the same is because an equation could be a function, or it could be a relation that's not a function. Right? The graph of an equation or an equation can possibly also be a function, or it might not be. If we talk about the graph of a function, well, we're restricted only to the definition of functions. Okay, now what are graphs? Where do graphs come from? Well, a graph is a picture. A graph is nothing more than a picture. Okay, a picture of what? Well, if we're talking about equations, equations have answers. Equations have solutions. When you have only one variable, there's only x's. There's only x's, or x squares, x cubed, square root of x. There's only x's in an equation. You're only going to get one answer, maybe two answers, a finite number of answers. But as soon as you start talking about equations with two variables, an x and a y, it's like, for example, let me give you one that we don't need to really write anything down to solve. Oops, sorry about that. Let's say, for example, x plus y is equal to 10. There's an equation. This equation has many, many answers, infinitely many answers. Any two numbers that add up to 10 is going to be an answer. And we could give those answers as ordered pairs, an x and a y. There's two variables, so each answer has to have two numbers in it. So 5 and 5, x equals 5, y equals 5. That's one answer. It's one solution. Or x equals 9 and y equals 1. That's a second different answer, different solution. X equals -6 and y equals 16, because when you add them up, you get 10. We could do this forever. Infinitely many options. They don't have to be whole numbers. X could be 0.25, right? And y could be 9.75, because they add up to 10, right? Etc., right? So if we start plotting these points one by one on a graph, we're going to start making a picture, right? A visualization of an equation. So the graph of an equation is a picture of all the answers. Once you have infinitely many points, you have the entire graph. The graph of a function, however, we generate this in a slightly different way. A function is not an equation. We can't solve a function. So an equation, a function is like an input-output machine. I talked about this in the previous video. What is a function? So the graph of a function, again, it's generated the same way, plotting all possible points. Go with this. The graph of an equation is the picture formed by plotting all possible points generated by that equation. And the graph of a function is the picture formed by plotting all possible points generated by the function. We just get those points in a slightly different way. In an equation, every point is an answer, is a solution to the equation. And in a function, every point is an input-output pair. Right? One number goes into the function, one number comes out of the function, and that's one point. And once we have infinitely many points, all of the possible points, that's what forms the picture or the visualization of that function. Okay, so let's put some of these definitions into action by solving a few specific problems. So the first one is going to utilize these first two definitions. Relations and functions. Every function is a relation, but not every relation is actually a function. So this is actually two problems. Problem on the left, problem on the right. So we're going to start off, ignore that. And let's say this relation on the bottom. Is it a function? Well, what this is saying is it's only four ordered pairs. I'm not calling them points because they're not dots on a graph, but we could graph these and make 4 points on the graph. The first point would be 4, 3. But is this a relation? So what this is saying is the number 4 goes with the number 3. The number 5 goes with the number 7. the number 3 also goes with the number 3, and the number 8 goes with the number 6. So let me write that. Let me draw that out in a slightly different way. I'll just go in numerical order, top to bottom. We have on the left, we've got a 3, 4, 5, and 8. And on the right, I've got two threes actually, 3, 6, and 7, but we don't need 2 copies of the number 3. We'll say 3, 6, and 7. So the x value of 3 goes to the y value of 3. The x value of 4 also goes to the y value of 3. The x value of 5 goes to the y value of 7, and the x value of 8 goes to the y value of 6. So you see here, two different x's are paired with the same y value. But that's okay, right? That's okay. If two x values go to the same y value, that doesn't contradict the definition of what it means to be a function. So let's say, I'll use green for this. This is okay. So no one x value is paired up with two different y values. So we say yes. It's a function. And now that we know it's a function, the domain is the set of all x values, and the range is the set of all y values. We're actually using 3 of the definitions on the previous screen, or the previous slide. So the domain would be the set of the numbers 3, 4, 5, and 8. All the x values that occur in this relationship. Relation is short for relationship. And the range is all the y values. You don't need to repeat y values. So there's a 3, a 6, and a 7. 2 separate sets. And the points, the way they're paired up, is how we connect these 2 sets. Now, let's look at the problem on the right. So let me get rid of that crossing out. So on the right, if we look at just the x values, there's a 4, there's a 2, there's a 4, there's a negative 4. All right, so I'll just go in numerical order because it doesn't matter down here. The x, we're just listing the x values. There's negative 4s, there's positive 2s, there's positive 4s. Those are the x values. So let me actually label this x, y, and x, y. Over here, the x's. Over here are the y values. So our y values, 3, negative 4, negative 6, and negative 5. We have 4 different y values. So I'll write them in also numerical order or ascending order. Oh, not negative 6 is the smallest, then negative 5, then negative 4, and then positive 3. Now, this first point is saying negative 4 goes with 3. Negative 4 is paired up with the number 3. Okay, next point is saying positive 2 for x is paired up with a negative 4. Okay, next point is saying positive 4 for x is paired up with negative 6 for y. And then the last point is saying negative 4 for x is paired up with negative 5 for y. Well, this is a problem. Because this negative 4, this one x value, is going to the y value of -5, and it's also going down here to the y value of 3. We'll say not okay. One x value cannot have two different y values. So this is not a function. It's still a relation. It's still a relation, but it's not a function. We could still talk about the domain. We could still talk about the range, right? The domain is the set of all x values. So there's a -4, there's a 2, and there's a 4, right? The -4 is repeated twice in the original problem, but we don't have to list it twice in the domain. And the range is the -6, the -5, the -4, and the +3. All right, so on the left, we have a function, even though two different x values go to the same y value. On the right, it is not a function because one x value is repeated twice. It goes to two different y values. Okay, so this is the method. This is the approach for, is this a function, yes or no, when we're starting with just a list of points. What if we don't have points? What if we have an equation? So basically, we're working with all possible points. All right, so number 2, is this relation, and remember, if there's an equal sign, there's letters and numbers, it's a relation. There is no situation where you have an equation and it might or might not be a relation. A relation is any equation. Function is more specific. So to determine if it's a function or not, we have to solve for y. Because y equals, I'll put this in quotes, y equals form, right? The y equals, solving for y, get y by itself. Y equals form is called function notation. Right, so this is the, how do I solve this problem? The question is this equation an actual function, yes or no? How do I solve it? Well, we have to solve for y. And this is something we've done before. So we need to get y by itself. Let's get rid of that x. So we have a positive x on the left, so we'll subtract x. So those x's cancel. In essence, we're moving the x from the left side over to the right side. So now we've got y squared is equal to 5 minus x. We want y by itself, not y squared. We want just y equals. So to get rid of the square, we have to square root both sides of this equation. And this is something we've talked about in a previous video. When you take the square root, of a variable, for example, the square root of y squared, we're taking the square root of the variable y squared. On the other side, we get two answers, a plus and a minus. So this is a problem. If we plug in one number for x, let's evaluate this. Let's say let x equal 4. Let x equal 4. What is the y value? So we're trying to figure out the point, 4 comma something. What is the y value? Well, if x is equal to 4, then we would say y is equal to plus or minus the square root of, instead of 5 minus x, we'll say 5 minus 4. So y is equal to plus or minus the square root. 5 minus 4 is 1. And the square root of 1 is 1. So y is equal to plus or minus 1. So we actually get two different y values for the same x value. So the answer here not a function. So basically, when you start with a relation, when you start with an equation and you solve for y, you isolate the y. If you get a plus minus, right? If you have to take the square root of both sides, if you get a plus minus, the answer is no, it's not a function. If you don't get a plus minus, then the answer is yes, it's a function. In this case, no, because of the plus minus. I'll highlight that because that is the reason why the answer is no, it's not a function. It's because of that plus minus. Okay, just a couple more problems to solve. Now that we're working with functions, right? We never will say solve the function. That doesn't actually make sense because there's nothing to solve for. This is not an equation. This is not f times x on the left. This is f of x. So when you see this and you read this out loud, it's read f of x, short for function of x. Well, we don't have to use the word f. It's not the word, the letter f doesn't mean function, but it's a function of x, right? So what that is saying, two things. One, the name of the function is the f function. Now we have to give them names because if we talk about two different functions, we can't call them both f of x. We may have in one problem an f of x and a g of x, or an f of x and a g of x and an h of x, right? Each function has to have a different name. And then the x in parentheses is saying x is the variable, right? So that's what the notation means, the f of x. So we're not solving, we can't solve functions. There's nothing to solve for. So what we're doing in this case is evaluating the function. So what can we do with functions? We could evaluate functions, we could graph functions, we could combine two functions together, we could add two functions, multiply two functions. We just can't solve functions. There's nothing to solve for. So the word evaluate, the word evaluate means replace, right? To evaluate a function means to replace the variable. Remember, a variable is a temporary placeholder, a temporary placeholder. So to evaluate a function means to replace the variable x with something else. Evaluate means replace. So I'm just erasing this because I need the board space here. So f of x is the function. When you see this is read f of 2. F of 2. Down here, in part B, this is read f of negative 2. And this third one, this is read f of negative a. In each of the three cases, we're doing the same thing. We're taking what's in the parentheses and replacing that for the variable x. So let's go part A, do that one first. Maybe we'll set them all up. So in each of these cases, right, that X, it's like a temporary placeholder. It's like an empty slot where we could put things into. Right, so in each of these three cases, we're going to take the function, but instead of the X, I'm doing 4 times something squared minus 1 over something squared. I'm just removing the X and putting in these empty parentheses. And I'm doing them all at the same time just to show you that all three of these problems are done exactly the same way. In the first one, we're putting in the number 2, where there was an X. In the second one, we're putting in a -2, where there was an X. And in the third one, we're putting a -a in place of the X. So now we have to simplify. 2 times 2 is 4. So on top, we get 4 times 4 minus 1. And on the bottom, we get 4. All right, so 4 times 4 is 16. We have 16 minus 1, or 15 over 4. So when we evaluate the function for x equals 2, plug a 2 in for x, our answer is 15 over 4. Second one's actually going to work out the same way, because -2 times -2, -2 times itself, when you square -2, that's also equal to 4. So we get the same thing on top, 16 minus 1, 4 on the bottom. So we get 15 over 4. And we don't have to only plug in numbers. We could plug in letters. We could plug in expressions. We could plug in anything. So on the bottom, we treat it the same way. We replace the x with a -a, and now we simplify. So 4 times, well, -a squared, that's -a times -a. Negative times negative is a positive. So that would give us 4 times a squared minus 1 divided by a squared. We don't need that dot there. We could write, with multiplication, we don't need a symbol, 4a squared minus 1, all divided by a squared. So that would be evaluating the function. The last two problems, we're not going to be doing any step-by-step mathematics. The next two problems deal with graphs, interpreting and understanding the graphs of a function. So 2 more problems. Number 4, use this graph. So this blue graph here is a picture of the function which we're calling g of x. Right? G of x is the function. We don't know what it is in terms of x's and numbers. We don't have an expression for g of x. We just have a picture of it. So part A is saying, find g of -5. That is saying is the x value is -5. What is the y value? Right, the x value is in the parentheses. We're saying, okay, replace x with -5. What is the y value? Same thing for part B. Replace x with +8. And what is the y value? So for the first one, -5 is right about here, right? We go left to -5, and when we go up to the graph, there's the point, and this point on the graph would be, oh, no, I want a red pen. Sorry, not a red highlighter. This would be the point, -5 for x, and +4, that's the vertical height, +4 for y. So g of -5 is equal to, this is saying, what is the y value? g of -5. What is the y value on the graph of g? When x is -5, the y value would be 4. Next problem, same thing. When x is equal to 8, so we'll go over to 8 on the x-axis and follow that down to the graph. That takes us to the point, let's say 8 for the x, and that takes us down to -2 on the y-axis. So 8 horizontal brings us down to -2 vertically. So g of 8 is equal to -2. This is saying if here's an x value, what is the corresponding y value on the graph? Part C is saying a value of x such that g of x is equal to 3. So the y value, g of x, is equal to 3. So let's look at the graph. 3 is right here. There's 3 on the y-axis. So if we go over to the graph, there's a point right there, but if I zoom in, it doesn't look like it's exactly 4, but I meant to have that graph exactly on the 4, so let's just say there's a point right there. And the x value of this point would be -4. So when x is equal to -4, the graph is up here at 3. And then there's also another point over here. When x is -6, the graph is up there at 3. So x, I don't say the x the value of x, I say a value of x. There's actually multiple. So when x is -6, the y value is also +3. And there's another answer because of this arrow right here. Right? We can't figure out that answer based just on this graph right now, but if we continue in this direction, there's going to be another point that has a y value of 3. Right, so we don't have all of the answers, but here's two possible answers to this problem. The last problem deals with our definition of domain and range, and I'm also going to introduce a couple one more term, intercepts. So we'll get to that. Well, let's talk about a and b first. Well, the domain of function f of x. So this is the graph of the f function. It says use the graph of f of x below to determine each of the following. We've got 5 parts. The domain of f of x. Well, the domain is the set of all x values associated with this graph. So all of these x values I just highlighted, and that goes on forever, all of these x values that I just highlighted appear somewhere on the graph. Right. This x value here is on the graph right there. This x value here is on the graph right there. Right? So these are all the x values that correspond to a point on the graph. So, and these x values over here, none of these correspond to any point on the graph. So the domain of this function will be all the x values starting with 0, going up to positive infinity. Right? We use a bracket on the 0 because 0 is part of our answer. All right, so let me use green for the domain. So the domain is starting here, and it's all these x values in this direction. Goes on forever because there's an arrow saying this graph is continuing on in this direction. Infinity always gets a parenthesis, never a bracket, because infinity is not actually a number. Now the range of the function is all the y values associated with the graph of this function. So the first one would be right there. That looks like -2. And all of these y values in this direction, and that goes on forever because the graph is moving to the right. It's also moving down infinitely far. So this green part of the x-axis, we say that's the domain. And none of these y values are anywhere on the graph until we get down to -2. So they're not part of the range. So the range of this function is all these numbers that are either equal to -2 or below -2. So that's going down to -infinity. Over here in green, that's going to +infinity. To the right is positive, to the left is negative. Up is positive, down is negative. So the range of this function, we always start smallest to largest. So the range is going from -infinity up to -2 and then stopping at -2. -infinity gets a parenthesis because, again, infinity is not a number. C and D ask for what are called the intercepts. Not intersect, intercept with a PT at the end. Intercepts are points on the axes. So an x-intercept is a point on the x-axis, and the y-intercept is a point on the y-axis. So this graph, so an x-intercept, we're looking for any point that has a 0 for the y value. To be on the x-axis, the y value, any of these points, the y value is going to be 0. Right? For the y-intercept, we're looking for points on the y-axis, So that means the x value has to be 0. Now, if we look at this blue graph over here on the left, there are no points on the x-axis. There are no points that have a y value of 0. We would say none. There are no x-intercepts. Y-intercepts, are there any points on the y-axis? Remember, this is the y-axis. Yes, there's one point. There's one point on the y-axis. An intercept is a point. Oh, I think I said y-intercepts twice. Don't want to do that. I don't need to do that twice. Domain, range, x-intercept, y-intercept. Now there is a point on the y-axis. That's the point 0, -2. This point right here. That first point that's on the y-axis, that is a y-intercept, has a y value of -2, an x value of 0. All right. So that is everything I wanted to cover in this video. This is obviously not everything we could say about functions and relations, but these are some of the highlights. The definition, what makes a relation a function or not a function? The domain and range of a function or a relation. What is the graph of an equation? Where does it come from? What is the graph of a relation or a function? Where do they come from? All right, so definitely more to talk about, but this is some of the general basics. Okay, that does it for this video. I hope this was helpful.